Okay, so we have strong acid, strong base. So we got HCl. Okay, and then we're gonna identify that it is aqueous, reacting with calcium hydroxide, which is also a strong base. Okay, and then you guys should be able to see the double replacement. So the H will bond with the hydroxide and you'll create HOH. But if you look at this, HOH is another way of writing water, right? H2O. So a lot of times you'll see it written either or, but just know HOH is the same thing as H2O. Sometimes they'll write it this way. Sometimes they'll write it this way. It doesn't really matter though. And we know from personal experience that water is a liquid, right? So we'll identify water as a liquid. And then the other compound will be CaCl2. And they just balance it by putting a 2 here, 2 here. And then based on the solubility rules, you should know that CaCl2 is aqueous. Okay. All right. Any questions about that? Hopefully it's not too bad. That's the molecular equation. We're going to write the net ionic in just a second. But I want to double check you guys are good. Everybody good with that? Okay. Before we do the net ionic, let's identify the acid and base. This should be your strong acid, HCl. Remember, you have to memorize that. And this is going to be your strong base. You also need to memorize calcium hydroxide and strong base. Yeah.
What rule means that CaCl is aqueous?
If you go up with Cl is usually soluble, and yeah, except for the exceptions.
Okay, so the +1 and -1 are always going to be inside.
Not necessarily. So this is based on the table up there. Again, you don't need to memorize that table. Yeah. It's just for these problems right here. We're just using those rules as examples. Okay, let's do the net ionic, and I'm actually going to skip the the full ionic equation. We're just going to go straight to the net, just to see what changes. Okay, so let's take a look at hydrogen. That's our first ion. Does hydrogen change its state of matter?
Yes.
Yes, it goes from something that's aqueous to a part of something that's a liquid, right? So we're going to have hydrogen in your net ionic. So we'll have H+. If we take a look at chlorine, does chlorine change its state of matter?
Yes. Or no.
No, it doesn't, because it's aqueous. And if you look on the right side of the equation, it is still aqueous. Yeah.
Don't you have to say 2H+?
Yeah, I'm going to balance it in a second.
All right.
But yes, it is 2H+. Okay, let's take a look at calcium. Does calcium change its state of matter?
No.
No, it does not. It's aqueous on the left side. It's aqueous on the right side. And then lastly, hydroxide is obviously going to change the state of matter. So you'll have for your net ionic equation, OH-, and that's aqueous, and that's going to produce water, H2O, which is a liquid. So both of these guys start aqueous, but then they become water, so they become a liquid. So here you will have 2 for each, and then that's going to be it. But if you didn't have the 2s, that's totally fine, because if you divide by the 2, it's the same thing. Okay, so you can leave the 2s on, or you don't have to. But either way, this is going to be your net ionic. So this is your net ionic, and then this is your molecular. Yeah, what's up?
So when the same amount of acid and base, the PSI would be 7?
Yes. Or the pH.
Sorry, pH. Why did they say it 0? Why they just said that?
It's a logarithmic thing. You will see that later. The reason why it has to do with the concentration of the ions. Yeah. Good question. You're jumping ahead like a semester though.
Oh
yeah. It's from the list you have to memorize. Yeah. You had to. It's the stuff you have to memorize. Yeah. All right. Any questions? Okay. And then just as a reference, you have to memorize this right here. So that's how we know if it's strong acids or strong base. Okay. And then if you don't remember, I gave you the tips on how to remember it. So just watch the lecture video from last time. All right, so that's enough of that stuff. We're going to move on to a different type of problem. And I hate these. But the AP test loves giving oxidation reduction questions. Another way that they're called, another name for them is redox reactions. Okay, so you might want to write that down. Oxidation reduction. Another name for them are called redox reactions. Okay, and redox reactions are types of reactions where electrons, they're transferred from one reactant to another. So it goes from one compound to another compound. And redox reactions are a way for us to keep track of how the electrons move. Okay. So again, redox reactions, they're reactions where electrons move from one reactant to another. Okay, so one of the most common redox reactions that we're familiar with is when iron rusts. So if you have like rusting on metal, that's because of a redox reaction. The electrons are being transferred. So we're going to talk about all that stuff in a sec, but we still need to do a little bit more definition stuff. So there are oxidation reactions and reduction reactions, and they always go hand in hand. It's like cause and effect. They go together. Now, you're going to have to keep in mind what those are. So I like to use the acronym oil rig. Okay, oxidation is loss, and it's talking about electrons. So whatever chemical loses electrons becomes oxidized, and then reduction is gain. Whatever compound gains electrons is reduced. That's how we describe it. Okay. So a compound loses electrons, it is oxidized, and then the one that it gives it to gains electrons, right? So it's going to be called reduced. All right, any questions on the definitions? Okay, we're gonna jump right into finding oxidation reduction, and we're gonna spend a good amount of time on this, which is why I extended the date of your test, because I want you guys to get a good handle on this, because we'll be using this quite often, and the AP test almost guarantees to have an oxidation reduction question. I personally don't like them very much, but it is what it is. All right, so one thing to keep in mind is oxidation and reduction, they go hand in hand, which means there's always, if there is one of them, the other one is going to be present as well, which makes sense, right? Because if one compound is losing electrons, the electrons have to go somewhere, right? And so oxidation and reduction always go together. And so we're going to take a look at an example right here. Ca, this reaction right here. You guys don't need to copy it down. It's where calcium is oxidized to 2+, and oxygen is reduced to O2. Okay, now we don't know how to find that yet, but here, what we're basically talking about is Ca is the compound that is being oxidized, and you guys don't need to write this down, because it is going to lose electrons, and O2 is going to be reduced, which means it's going to gain electrons. Okay, so the point of this is to show you guys whenever you have an oxidation redox reaction, one compound has to get oxidized, and the other one has to get reduced. Okay, so just keep that in mind. They go together. All right, now so the way that we're going to find out which one gets oxidized and which one gets reduced is we need to calculate something called an oxidation number. Okay, and as you can see, there are a lot of rules. And yes, you need to remember these rules. Okay, but it's not as bad as it seems. Okay, so we're going to go through them one by one, but just make sure if you have any questions, you let me know. Okay, because I can empathize. I hate redox. Unfortunately, it's a big part of the test. Okay, so there are a couple rules. The first oxidation number rule is that any atom in its elemental form has an oxidation number of 0. Okay, so an elemental form is the most basic form of an element. It's basically how it's found in nature. And if it's in that form, it's going to be 0. So for example, hydrogen is mostly found in the environment as H2 gas. In this situation, hydrogen has an oxidation number of 0. You got an example with phosphorus right here. If you have any metal and it is a solid, that is also going to be an oxidation number of 0. Okay, just make sure you guys jot that down somewhere. Okay, any metal, solid metals are going to have an oxidation number of 0. Okay, H2, O2, N2, these are the most common diatomic gases you'll look at. These guys all here also have an oxidation number of 0. Okay. So hydrogen in H2 gas has a 0 for oxidation number. Oxygen in O2 gas has an oxidation number of 0. Any metal that's a solid is going to have an oxidation number of 0. That's what an elemental form is. It's like the most basic form an element is found. Okay. Any questions on that? Yes.
So unless it's aqueous, it's 0. That's what you're saying?
Not necessarily, because you can have like HCl gas, and in that situation, that's not the elemental form. Yeah. Yeah. So you can have other compounds that are, but a lot of times if it's aqueous, it's gonna have a, it's not gonna be 0 though. Yeah. Solid will be 0 though, most of the time.
And then gaseous, like
depends. Yeah. Okay, you guys ready for number 2? All right, number 2. This one is easy. Any monatomic ion, the oxidation number is what its charge is. That one's easy. So if you have like K plus right here, right? The charge is +1, so the oxidation number is +1. Super easy. S2 minus, charge is -2. The oxidation number is -2. Okay, so this is the easy one. Okay. The oxidation number is going to equal its charge. All right, any questions about that one? That's probably the most straightforward. And again, oxidation numbers, we're going to talk about how they're used in redox reactions, but oxidation numbers are used to find out which element gains and loses electrons when they react together. Yeah.
So why would S2 minus have -2 oxidation charge while like the element just
Because it's lost electrons. Yeah, or gained electrons. Sorry, it's gained electrons. Again, this all has to do with how electrons move. So yeah. Okay, let's go to number 3, and that's kind of a very annoyingly worded rule, but nonmetals usually have negative oxidation numbers, but they can sometimes be positive. Okay, so usually they're negative, but they can sometimes be positive. So this is a very important one to remember. This part 3A, this is the one that usually controls the reaction, okay? So oxygen, 99.9% of the time will have an oxidation number of -2. Okay, so if you see an oxygen inside of the reaction, most of the time the oxidation number will be 2. Okay, the big exception that they might try to trip you up is peroxide, which is an O2 2- ion, and that's where oxygen has an oxidation number of 1. Okay, so just to summarize, most of the time, oxygen, if you see oxygen in the reaction, it's going to have an oxidation number of -2. The only exception is if it's in this form. If you see this ion, the oxidation number for oxygen is going to be 1, okay, because there's 2 of them. So it's -2, and they add up, so it's -2 right there. Just keep that in mind. I know you guys are getting confused now. Just remember this one right here, okay? Oxygen is -2. And there's one exception, one major exception. You guys can see why I don't like this very much, right?
Yeah. Does it have any practical uses?
It does. This is going to be very important in the last 3 units of the course. Yeah. Super important.
It's not that bad. It's just like
Yeah, but then if you look at the 3rd last unit, it's like the longest unit.
how long are we gonna spend?
Like a month. on 1 unit. All right, let's move on. Okay, hydrogen usually has an oxidation number of +1. Okay, hydrogen is +1 when it's bonded to non-metals. But when it's bonded to metals, hydrogen is -1. Okay, yeah, hydrogen can be plus or -1. Super fake.
So it's like 2 things.
It is. When it's with non-metals, it's positive. When it's with metals, it's negative. Yeah, it's just B. It's just B. I'm just reading B. Hydrogen is usually +1. So when hydrogen is with a non-metal, so for example, if hydrogen is with chlorine, right? Hydrogen has an oxidation number of +1. But when it's bonded to a metal, so for example, like lithium, hydrogen will be -1. That's what that rule means. Okay. Yes. When they are solid, when they're in solid form, yes, yeah. But when they're aqueous, no.
So that's why hydrogen is technically, that's why that.
Yeah,
like
that's correct. It's a non-metal. Yeah. All right. So in addition to oxygen, this is also an important one. Fluorine is always -1. Always, always, always. And there's no exceptions to this. So this is a rule that you can actually trust in. You guys having fun yet with oxidation numbers? Yeah, we're gonna spend a lot of time getting this, so it'll be better once we start doing practice problems. We just have to go through these rules first, and then once we apply it, it'll be a bit easier and make more sense. It's not as bad as it seems. Okay, you guys ready to move on? So fluorine is always -1. All right, now the next one for 3D, it's going to be about halogens. So halogens are compounds that are in the second to last column of the periodic table. So it's the one with like F and Cl. So if we take a look at it, halogens are right here. Group 17, these guys right here. Okay, halogens, they're going to be -1 most of the time. Okay, other than F. F is always -1. Except when halogens are with oxygen. Because remember, oxygen is the controlling one. Oxygen is always going to be -2. Yes.
Like bromine.
Yeah, like bromine, chlorine, iodine. Yeah. Okay. So halogens are -1 most of the time, except when they're with oxygen, because oxygen is going to pretty much overpower them. Yes.
Does anyone know why it's like this, or is it just like
It's just a system that we made up to keep track of like the way the electrons move.
that's how it works?
Yeah, this isn't this honestly not a real thing. It's just a way that we measure oxidation, like how the electrons move. The only real thing is that electrons move. This is how we just keep track of them. Yeah.
So it could be like a different method.
I guess, but you would need a completely different numerical system then.
So your oxidation.
Okay, so let's go to rule 4, and I think this is the last one. And this one's pretty simple. Okay, the sum of all the oxidation numbers on an atom in a compound is equal to its charge. Okay, so what that means is if you have sulfate, for example, the charge on the whole molecule is -2, right? That means if you add up all the oxidation numbers in sulfate, it should equal -2. If you have a neutral atom like CH4, which has no charge, you add up all the oxidation numbers, the oxidation number for the whole thing should be 0. Okay? All right, and now we're going to do a couple practice problems. I'm going to go through them very slowly with you guys because I know that was a lot of info. So yeah, we'll go through them together. And we'll do a lot of oxidation reduction practice pretty much for the rest of the class period. All right. You guys ready to try a couple?
Sure.
Any questions on any of these rules? Any clarification that you guys need? Okay. So my recommendation is as we do these next couple practice problems, we're not going to skip any of them. I would say on your Chromebook, have these rules, be open to these rules and look at the problems on the screen. That way you can refer to these rules as we're doing the problems, okay? All right. You guys excited?
Sure. Yeah.
I'm so excited. Okay, so what we're gonna do is we're gonna determine the oxidation number of sulfur in all 6 of these compounds down here, okay? So I'm gonna do a couple of them with you guys, and then I'll do the first 3 with you guys, and I'll have you try the other 3 on your own, okay? So let's start with A, H2S. So we are looking for the oxidation number of sulfur, so we don't know what sulfur is, okay? In any of the rules, do we have any information about the other atoms inside of this compound?
Okay.
Hydrogen, yeah, we have a rule about hydrogen. What's the rule on hydrogen?
When it's with a non-metal, it's 1+.
Yes, so if we take a look at the rule, so I'm gonna pull it up here. We say, where is it? Hydrogen. Yeah. Hydrogen, when it's with a non-metal, like sulfur, it is +1. Okay, everybody good with that?
Yep.
So that means that hydrogen here is going to be +1. Okay, but how many hydrogens do we have?
2.
2. So we have 2 hydrogens and each of them are +1. Okay, now if you remember the rule, if the atom or the molecule is neutral, when you add up all the oxidation numbers, it needs to add up to 0, right? So what does sulfur have to be in order for it to be neutral? -2. There you go. So there you go. That's the answer to part A. Sulfur here has an oxidation number of -2. Yes.
It's like, you know how like sometimes when you're like making ionic compounds, like you do like that process.
Yeah.
Isn't that the same?
So it can work sometimes, but it won't work all the time. We'll see why in the following examples. Yeah, so I'd say for oxidation numbers, you just use what we talked about. Okay, let's go to part B. Now for part B, we got S8. Okay, which means since this is neutral, what does the total charge of all of them combined have to be?
0.
0. So this needs to equal to 0, but you have 8 sulfurs, which means what do all the sulfurs have to be? 0. So this is actually the elemental form of sulfur, and we can tell because it adds up to 0. So this is the elemental form. And you guys don't need to memorize that. Okay, but all of the sulfurs have an oxidation number of 0. All right, hopefully this is making it a little bit better. Yeah, maybe. Who knows? Okay. Let's move on to C. So we got SCl. Now we're looking for S, so obviously we probably don't know S. Do we have any rules about Cl though?
Yeah, it's an halogen, which means -1. Hence, it's not oxygen.
Yes. So halogens other than fluorine is -1. So the only exception is when it's with oxygen, and chlorine right here is a halogen. So chlorine is going to be -1. Everybody good with that? Does that make sense? So each chlorine is going to be -1. So what does sulfur have to be? +2. That's correct. Okay. Is this a little bit better now as we do the problems? Okay. Yeah, I know just looking at a wall of rules just makes it a little scary, but okay, so we're actually gonna do F together, and I'll have you guys do D and E on your own. But let's take a look at F. Okay, now if you notice, what's different about F compared to the other ones we did?
It has a charge.
Yeah, so that means everything combined has to equal to -2. Okay. So we're looking for sulfur. Now, luckily for us, we have oxygen, right? And what's the oxidation rule for or number for oxygen?
-2 usually.
Yeah, -2. Okay, in all cases, unless it's peroxide, and this isn't peroxide. So you have 3 oxygens. Okay, -6. What does sulfur have to be? Yeah, what's up, Ford? It has to be +4. Why does it have to be +4? Exactly. Yeah. It needs to be positive 4 because it needs to sum up to negative 2. Thank you. So proactive. Scholar. All right. I'll give you guys a couple minutes now. Do you guys feel a little bit more confident in doing these?
Yes.
Okay. I'll give you guys about 3 minutes. See if you guys can do D and E with the person next to you. Double check with them to make sure you guys are on the right page. We'll go over and we'll do a couple more examples. Okay. All right. So let's take a look at E. So obviously, we got 4 oxygens, so that's going to be -2, -2, -2, -2, and it needs to sum up to a total oxidation of -2. So can someone raise their hand? Yeah, yeah, Cash. What does sulfur have to be? Yeah, +6. There you go. So you guys can tell that even though it's very similar to sulfite, right? Sulfate and sulfite, but the oxidation number on the sulfur is going to be different because of the number of oxygen. Okay. Okay. All good with that one? Okay. Let's go to part D. Now, part D has a little trick to it. Now, the sodiums might make it look a little confusing, right? But if you guys take a look at this right here is a polyatomic ion, right? And so we already know automatically that polyatomics are just kind of their own standalone ions. If you take a look at this, it's pretty much the same thing as sulfite right here, right? So that means the sulfur here is going to be +4. Okay, so let me go a little backwards on this, okay? So if you take a look at this compound, this is, you guys can tell this is an ionic compound, right? It's made up of 2 sodiums and a polyatomic ion, sulfite. Okay, so we got these ions right here. Now, we already know about sulfite because of this example right here, right?
Yeah.
And so we don't even need to worry about the sodiums here because this is a polyatomic. Polyatomics, if you remember, are chunks that like to stay together. So this compound right here is going to be -2 no matter what it's bonded to. It could be like K2SO3. It could be CaSO3. This is still SO3. It's still -2. And then we found out here that sulfur is +4 because it has 3 oxygens, -2, -2, -2. And so for here, sulfur is also going to be +4. Yeah.
Hypothetically speaking, what would the sodium like
By itself,
yeah, like right.
it's going to be +1 because of the charge. Yeah.
So on the peroxide, if it's 2 of them, would that mean that each oxygen is 0.5 values?
No.
How does it work now?
Peroxide?
Yeah.
It'll be, the oxygens will be -1, -1. The hydrogen will be +1, +1.
Oh, so we overall have a positive.
Yeah.
Okay.
Yeah. Another way you can take a look at this problem too, guys, is if this was too complicated. Okay, we talked about how rule number 1, right? If I look at rule number, rule number 2, any monatomic ion, the oxidation number is its ionic charge, right? So if you take a look right here at Na, we know that Na is +1, right? This is made out of +1, +1. So what's the oxidation number for sodium here? Yeah, +1. So both of these sodiums are +1. So if you wanted to do it the long way, you can. It'll be +1, +1. We know that oxygen is -2, -2, -2. Okay, sulfur and sodium needs to balance this out, so it has to be +4 because it's +6 balancing out the -6. That's another way you can look at it. So a lot of times, if you just look at the ionic charge, it can kind of help you quite a bit. Just remember oxygen is -2. Okay. Any questions? Do you guys feel a little bit more confident doing these? Maybe. Maybe not. Okay, we'll do more practice then. Okay, so these are, I guess I'd say a little bit trickier, maybe. Okay, I want you guys to find the oxidation state of the underlined elements. Okay. If you have trouble reading any of these, please let me know and I can write it bigger or clarify. But take about 5 minutes, see if you guys can do these on your own, and then we'll go over it and then we'll move on to, I guess, bigger oxidation number problems. Alrighty, guys, let's start going over these. Again, if you're still working on it, just check your answer at the end and let me know if you have any questions. Let's start with part A. So we got 5 oxygens, right? We know oxygen has to be -2 So that means all of the oxygens together are going to be -10. Any questions on that? Chilling? Okay. We got 2 phosphoruses. So what does phosphorus have to be to balance out -10? 5, yeah. +5. Because if you have 2 of them, you balance out the oxygen. So phosphorus will be +5. Okay. Does that make sense, everybody? All right, let's take a look at part B. We got NaH. Okay, now one of our rules about hydrogen, if you guys remember, if hydrogen is bonded to a metal, what is the charge on hydrogen? -1. And it also makes sense because sodium, right, is going to be +1 when it's on its ionic form, so it needs to balance out with -1. Okay. Yeah, what's up?
Oxidation state is what it looks like.
Yeah, so we're gonna see what it means once we do the reactions, but yeah, it's just basically like I don't really know how to describe it. It's just the oxidation number that it has. Yeah. All right, let's go to the next one. This one's very similar to the first one. We got 7 oxygen, so it's gonna be a total of -14. It needs to add up to -2. So what does chromium have to be?
6.
Yeah, +6 each. Because if you have 2 + 6s, that's +12. -14 is going to balance to -2. And it's because of this right here. So far, so good, guys? All right, let's go to the next one. Part D. If you remember bromine, bromine is what? -1, because the halogen, exactly. Halogens, they have a oxidation number of -1. So we got 4 of them. So what does tin have to be to balance that out? +4. Dude, this is easy peasy for you guys. I'll make this class harder. All right. Now this one was a tricky one. How many of you guys put -2? Nobody? Or did everyone put -2? All right, somebody who didn't put -2, what did you get for oxygen? Yeah. -1. Carm, what you get? -1? It is -1. Good eye, guys. This is peroxide, O2 2-. And the key is that barium, what's barium's MCI?
2+.
2+. So that means it doesn't make sense for there to be 2 oxygens, right? Unless it's peroxide. So this right here was -1. I wanted to end the last one by tricking you guys. But if you got it, great job. Okay, guys. You guys ready to do this in a reaction now?
Yeah.
It's actually not too bad because now you'll actually be able to see why we're doing these numbers instead of just calculating them. So let's go on to the oxidation numbers, but in the reaction. So now that you guys are super experts in finding oxidation or numbers, now we can actually tell if something is being oxidized or reduced, if it's gaining or losing electrons, okay? So I'm going to do 4.12 with you guys, and I'll have you do 13 on your own, but let's do 12. So we have Mg. Now, what's the oxidation number for Mg right here?
2+.
It's 0. It's just by itself. It's solid form, so it would be 0. Okay, so far so good? All right, let's move on to the next one. Here you should be able to tell that hydrogen is +1, right? Because it is with a nonmetal, which means chlorine needs to be -1. Everybody good with that?
Yeah.
Okay. Let me give you guys about 30 seconds, so not a lot of time. I want you guys to find the oxidation numbers of the other side. Okay, so I'm going to draw a little line right here to split the reactants and the products, but take about 30 seconds, find the oxidation numbers for the products. All right, guys. You guys think you can give me the answers now?
Yes.
Okay, Grant, give me magnesium.
2 plus.
Yeah, magnesium will be 2 plus. Okay, can somebody raise their hand and give me the chlorines? Yeah. Yeah, chlorine's going to be -1. And again, they balance each other out to get 0. And then can somebody raise their hand and give me hydrogen? Yeah. Not -1, actually. Yeah. Yeah, 0. This is one of the examples I gave earlier. This is the elemental form. So I'm sorry if I tricked you. Yeah. Yeah, I'm just splitting the reactant and the product side. Oh, that's just how I write 0. Why? Does it? Ah, sorry. Sorry if it bothers you. Does it bother you? Is it bothering you? Sorry, I'm a bully. Okay. Okay, everybody good with those oxidation numbers? Okay, now let's go back to our original definition about oxidation reduction. Remember oil rig? Yeah, oil rig. Okay, Mr. O is very anti-green energy. So we're all about oil. Okay, so oil, so oxidation is loss. I'm just kidding. Okay, oxidation is loss. So it's losing electrons, and reduction is gain. So let's figure out which element is losing electrons and which one is gaining electrons. Okay, so let's take a look at magnesium. Okay, so if you take a look at magnesium, the oxidation number went from 0 to +2. Now, stop right there and think about it.
Right there.
The oxidation number is becoming more positive, right? So if something becomes more positive, is it gaining or losing electrons? It is losing electrons. Think about it this way, guys. Mr. O is an electron. I am a very negative aspect of your life, right? Once you are done with this class and you lose Mr. O, you are going to get more positive, right? You're going to go from 0 to +2 when you get rid of Mr. O. So here we are losing electrons. And if you are losing electrons, are you being oxidized or reduced? Oxidized.
Mr. What if I got conditioning after? Wouldn't that make it more negative?
Huh?
What if I got conditioning after? Wouldn't that make it more
I guess so, yeah. Whatever negative is in your life. So here, the chemical that is being oxidized is magnesium. So Mg is being oxidized. Okay, does that make sense, guys? Okay, so here in this reaction, by using the magic of oxidation numbers, we can tell which compound is gaining and which compound is losing electrons. Okay, now in this unit, we're not going to go too in depth, but this is actually how batteries work. Okay, our whole, battery technology is dependent on some compounds gaining electrons, some compounds losing electrons, and that's what creates a flow of electrons, which we call electricity. Okay? Yes.
So if that's +1 -1, and that's +2 -1, where did the extra electron come from? Or does the
Because there's 2 of them. Yeah, we didn't because it's balanced. So it'll be +1 -1 -1.
Oh yeah, yeah.
I just didn't write it because I wanted for each element, but you get the point, right?
Can by the way, can electrons ever like dissipate and like
No. They're matter. Yeah, you can't destroy matter. Okay, except with antimatter, but that's beyond the scope of this class. Okay, so let's go to the next one. Hydrogen. Hydrogen goes from +1 to 0. So did hydrogen gain or lose electrons? Yeah, it gained electrons, right? It joined AP chemistry. It was happy, and then it met Mr. O, and now it got a little less happy. Okay, so that means that hydrogen is being reduced. Okay, does that make sense, guys? So basically, magnesium is giving its electrons to hydrogen, and that's how the reaction takes place. Okay, that's it. That's why we talk about oxidation reduction. It's to show how the electrons move from compound to compound. All right. With that example, do you guys feel like you can do 4.13? So I'll have you guys try 4.13, and then we'll take our break after that. Okay. So do 4.13. I'll give you guys about, I know, 12. We're not there yet. I'll give you guys 4 minutes to do that, and then we'll take our break afterwards. Okay, so try 413. 13. Alrighty, guys. So I'm just gonna, well, I mean, we don't even really need to find the oxidation numbers, right? It's already given to us. +1, +4, +3, +2. Anyone have trouble finding those? Yes? It's okay. All right. It's okay. We love you just the way you are. Deficiencies and all. Okay. So we're going to go to chromium. So Cr. Hey, everyone has deficiencies. My biggest deficiency is my height. Okay. Anyway. Chromium. So it goes from +1 to +3. So it got a lot more positive, right? So if it became positive, did it gain or lose electrons? It lost electrons, right? So it lost electrons, so which means it is being oxidized. So chromium is being oxidized here. What? Like that? I don't know. Why are you looking at my face so like attentively? Why are you smiling right now? Do you like this class? Why do you like this class so much? I gotta make it harder now. You guys can say thank you, Jimmy, on your test, okay? Okay. All right. So obviously here it became more negative, right? Because it went from +4 to +2. So it's going to gain electrons. It took AP Chem again. So 10 is going to be reduced. Okay. Alrighty, guys, let's take our break real quick. And then if you have questions, please let me know, and then we'll move on after you come back. Alrighty, guys. So take a look at 14. So we start with AS. So it's a solid metal, right? Or metalloid. And so what is the oxidation number on AS?
0.
0, yes. This is 0. Okay, remember, solids will be 0. All right, we take a look at Cl2, and it's a gas. Okay, so this is actually the elemental form of chlorine. So if it's the elemental form, what's Cl gonna be? 0. So on the left side, we got 0, 0.
Yeah.
Okay, let's go to the right side now. So we know that Cl is a halogen, right? So what is the oxidation number for a halogen? -1. And if there are 3 of them, what is AS on the product side? +3, because there are 3 chlorines. Okay, so just be careful of that. I know there's so many numbers to keep track of now. It's how many of the elements, how many of the molecules, the charges, but yeah. What's up?
Well, like, what about like the
Doesn't matter. Doesn't matter.
matter.
Okay, so everybody good with these oxidation numbers, how we got them? Okay. Okay, so this should be pretty easy then. Let's take a look at AS. So if we take a look at AS, it became very, very positive. So did it gain or lose electrons? It lost electrons, which means that it is oxidized, exactly. Scholar. Okay, let's go to the other one, which means obviously since this one lost electrons, this guy gained electrons. And if the guy gains electrons, it is being reduced. So AS is being oxidized, chlorine is being reduced. Okay, that's it. That's about as hard as redox will get until the second semester. Okay, so if this is pretty easy, I know like obviously you might make mistakes here and there, but if you understand the concept and you feel confident doing this, you're in good shape for redox. Okay. All right. Let's move. Yeah. You guys want to do 4.15? Yeah, let's do 4. Wow, you guys want to do practice problems? All right, go ahead. Yeah, go ahead. Try 4.15.
Yeah, we don't want to fail the test.
Okay, so 415. The oxidation number for Hg2 plus is obviously +2. Fe is iron. Solid iron is 0. Okay, Hg right here. Hg2. Now you might look at this and be like, what could it be? We don't know about the elemental forms. However, what's the total charge on the entire molecule?
0.
0. So that means if you got 2 Hgs, what does the oxidation number have to be?
0.
0. So this is 0.
That's good.
Okay. And then obviously Fe will be +3. Okay. So far, so good. Now, I'm gonna let you guys know right now, even if you didn't know what Hg is, you can actually just skip it and figure out if it's being oxidized or reduced. Because if you take a look at Fe, is Fe being oxidized or reduced? Oxidized, because it becomes super happy, right? If it becomes happy, it lost electrons, which means it is being oxidized. So if Fe is being oxidized, what does Hg have to be? It has to be reduced. So even if you don't know what the oxidation number is here, right? You might be like, that's a little weird. You can still figure out if it's being oxidized or reduced by knowing the other one. Okay? There's going to be usually one oxidized, one reduced.
Is this as hard as the oxidation level thing?
At least for now. Yeah, it'll get harder later though.
Like AP Chem, AP
Yeah.
Mhm.
All right, everybody chilling with this?
Yep.
So we're done with redox now, for now. But I think the next part you guys will find a little bit better because it is, you guys are more familiar with it. Is chemistry fun though? All right, so now we are going to be talking about concentration. Now, not the concentration where you're focusing really hard, but we're going to be talking about concentration of solutions. Easiest way that I think we understand this in everyday life is how this is talking about how strong a solution is. Okay, so I know that none of you guys are interested in alcohol at all, right?
No.
As high schoolers, no interest in alcohol. You guys will all wait till 21 to have your first sip of alcohol because of America. This is US rules, okay?
Unless it's provided.
Yeah, unless you go to a different country.
Oh yeah.
All right. I'm glad that you guys are so proud of your backgrounds. Okay, anyway, so concentration is just basically a measure of how strong something is. Now, I know that you guys don't know a lot about alcohol, but let's just think about hypothetically some things you guys might have heard with no personal interest, right? So you have different drinks have different amounts of alcohol in it, right? So for example, beer, does it have relatively a lot or a little? Not too much, right? But if you got something like whiskey, okay, which one has more alcohol in it?
Whiskey.
Whiskey has more alcohol. So usually when you think about whiskey, you think of it as stronger than beer, right?
Yeah.
So whiskey would be more concentrated, okay, than beer. This is less concentrated in terms of alcohol. That's what concentration is, okay? Whiskey has more alcohol per volume than beer has alcohol per volume, which means that it is more concentrated. Great. But you shouldn't because you are underage.
It's only like $3.
You're in America now. All right. Anyway, does that make sense though? The general concept. Okay. So the way that we measure concentration 99% of the time in chemistry is something called molarity. Now make sure you guys write down this formula. Okay, easy way to think of this is capital M is the symbol for molarity. It's the moles of whatever you're looking at, whatever's dissolved, divided by the liters of the solution. Okay, so how many moles are dissolved per liter?
Yeah.
Yes.
So it's like counting the solute in the
Yeah, per volume.
So-
Yeah,
So it's basically how many moles of ethanol are dissolved per mole of solution.
exactly. How do you know it's ethanol? How do you know it's ethanol?
Because I had this in my chemistry class.
Okay, so let's take a look at 4.16 and I'll write the formula up here if you're still copying it down. Okay, but molarity is measured in moles divided by liters. So here we are comparing two different solutions. Okay, we got a solution that's 500 milliliters with 21 grams of NaF dissolved in it, and then 100 with 10.5. I want you guys to take a second to calculate the molarities using that formula. Do you guys want me to try one for you first? Okay, you don't need me. All right. So try it out. See if you can find the molarity of solution A and solution B, and then compare which one is more concentrated. Okay, take about maybe like 3 minutes to do that. Okay, so first thing you want to do is obviously convert the grams into moles, right? Because to find molarity, we need it in terms of grams. So we're going to do 21 grams for, or let's do solution A first. Solution A, 21 grams of NaF. So you're going to need the molar mass. So you go to the periodic table and add them up. So 23 plus 19 is 42 grams in 1 mole. Okay, you calculate that out and you should get 0.5 moles for NaF. Everybody good? Okay, now we're going to plug this into the molarity formula, and we know that molarity is equal to moles divided by liters. So make sure you can move the 0 3 times. So it'll be 0.5 liters. So you should get a total of 1 molarity. So solution A has a concentration of 1 molarity. Okay. Make sense? Alrighty, let's take a look at solution B. Same thing with solution B, except this time we have 10.5 grams of NaF. Do the molar mass, same molar mass, 42 per 1 mole. And this time you'll get 0.25 moles. Okay, so you have less solute in solution B. Okay. However, because the volume is also smaller, it'll be 0.25 moles divided by 0.1 liters. Okay, you're going to get 2.5 molarity. All right, so answer to the question, which one is more concentrated? B. Solution B will be more concentrated. Okay, the point is, even though technically solution A has more solute, because the volume is bigger, it's also going to be less concentrated. All right. All right, any questions on that?
No.
Yes.
Does it have to be in a homogeneous mixture in order to have molarity?
Great question. Technically no, but usually yes. We're gonna be looking at homogeneous stuff, because if you have like chunks of it in there, it's kind of hard to measure the actual molarity. Okay, we are gonna do one more question. I know you guys were distracted, but it's okay. We're gonna skip to 4.18. Okay, and I am going to give you, since we only have like 4 minutes left, I'm gonna give you guys 2 minutes. And then we are going to go over it together. So this is kind of me testing how good you guys are at reading the problems. So take about 2 minutes, try to solve this out, and then we're gonna go over it together. We're looking for the molar concentration of each ion. So let's take a look at this compound, because we'll figure out, that'll let us figure out the ion. So calcium nitrate, you guys should have gotten this formula or mentally noted this formula. Everybody good?
Yeah.
Okay, now it's asking for the molar concentration of each ion. Okay, so if we take a look at this ionic compound, how many calcium ions are there? 1. So it's going to be 1. And how many nitrate ions are there? 2. There's going to be 2. So let's think about this logically. If this solution of calcium nitrate is 0.12 molarity, okay, what's the molarity of the calcium ion?
0.6.
Not 0.6, just
Sorry,
calcium.
0.06, my bad.
So each calcium nitrate ion breaks up into 1 calcium. So this is going to break up into 1 Ca2 plus, and it's going to break up into 2 nitrates. So if you take a look at the ratio, how many Cas come out of calcium nitrate? 1. So that means it's going to have the same concentration as the original solution, because each one of these breaks into one of this, right? So if I was, for example, cutting off your head, right? And I cut your head off, how many heads will come off of you? 1. So it's a 1-to-1. Okay.
No, yeah.
So nitrate, though, since you get 2, what's the molar concentration of nitrate? 0.24. Because you get 2. We'll go over that when we meet again. I'll see you guys.